Good morning. I hope you're all having a great morning, and I'm thrilled to introduce Paul Larios. Paul graduated from civil engineering in 2013, and he is going to talk to us about the work that he's been doing. And I'm going to let him tell you that, but it's just a thrill to have him back, to kept connected over the last 9 years. And I'll turn it over to you, Paul. Thank you so much for being here.
Thanks so much for having me, Dr. Maston, once again. Always a pleasure. I'm happy to talk to some fellow Spartans. Hope everyone is acclimating to the fall semester, enjoying the October campus. Kind of wish I was out there. I will be able to attend the football game at Rutgers in New Jersey this Saturday at least, but I'm still very jealous of all of you guys. So yeah, 9 years ago, I was in your seats taking Dr. Maston's course, and now I'm back in New York, where you can see pictured. That's where I'm from. That's the Ashokan Reservoir, which is New York City's largest water source, 123 billion gallons. And I will talk about that some more on some projects I've worked on. It's about 10 miles away from where I live and work in Kingston, New York. So about me, I got my PE in 2019. I did a 1-year MEng master's program in environmental and water resource systems engineering right away after MSU at Cornell. And then I came straight to work for the family business that my grandfather founded. My dad is currently president of, and I'm still here now. And then as far as today, I guess you guys have had fluids, but not hydraulics probably. So I'll go through just one slide quick. I won't get too technical, I promise. And I'll talk about my grad school experience, my experiences as a professional, job searching, interviewing, different career paths you can take, and some projects of interest for this course, and then some hopefully some useful advice for you guys. And if you guys want to use the chat for any questions, I'll keep that open. All right, some quick fluids. Continuity equation, very important principle here. It's the conservation of mass. So the top right graphic, flow in is going to equal flow out. So if anyone has a guess which velocity is higher, V1 or V2 in that graphic, I'll leave it into the chat for the first one to get it here. Good job. Yeah, so when the area decreases, you're going to have faster velocities to balance out the mass. Then, another staple of fluid mechanics is the conservation of energy, Bernoulli's equation, which consists of pressure head plus elevation head, velocity head, plus a head added by any pumps. And that's going to equal the same on the other side, plus head losses. Important HGL, hydraulic grade line. That's the height the water would rise in a tube. Elevation plus pressure head, so ignoring velocity head. And that's very important for treatment plant design. I'll I'll show you guys a profile of the water surface level throughout a treatment plant I designed, and to make it work, you're tracking the HGL throughout the plant, making sure that you have that level where you need it. Then we have some flow regimes, laminar versus turbulent. Turbulent at higher velocities where viscosity is not really doing anything, and you're getting some turbulent eddies like in B here with the chaotic streamlines compared to the streamline shown in A that would be laminar flow with the lower Reynolds number. Yeah. Head losses, so mainly friction losses, drag, so from pipe friction on the wall, which you would use Moody's diagram. And then minor losses, which the bottom right graphic shows well. Those are just flow expansions or contractions due to irregular geometry, fittings, valves. And then Manning's equation for open channel flow, I'm sure you guys all know. And then pressure, depth. Obviously, pressure is going to increase with depth, H, and a good conversion is 1 foot of water is equal to 2.31 psi. I use that quite a bit. So hopefully that was just a quick freshener. So graduate school, my first step, I was dead set on attending grad schools throughout undergrad. It was kind of a goal of mine to have a high GPA and get into a prestigious school, probably come back to the Northeast where I'm from. But my first step, I brought a list to Dr. Maston because I knew she would have an idea of, strong programs, where the good faculty and research is going on, and she pretty much went through my list, and I ended up applying to those ones listed: Cornell, Purdue, Virginia Tech, Manhattan College, and University of New Hampshire after taking the GRE. So the GRE in 2020 was waived for a lot of schools, COVID related. I'm not sure if that's still true. When I took it, engineering schools really just looked at your quantitative score, and the math on there is pretty much just SAT math, high school levels. You just have to kind of reteach yourself some quick tricks and beat the clock on that. But yeah, I was looking for 1 year masters of engineering programs that are geared towards professional development rather than more of an academic MS program, PhD track type of thing. So those are the schools I ended up with. I ended up getting into all of them, and I went to Cornell mostly because of the Agua Clara program, which I'll talk about. One thing to keep in mind is you can always go to work, and a lot of the big firms will pay for you to go back to school, which is nice, but then a lot of times you're working and then going to night school. It could just be a lot, I'd imagine. I wanted to get it over with. And I'd say if you're going to commit to grad school, it'd be great. I mean, that's one advantage. If you do go to work first, I mean, you would want to know exactly what you're going for. How did I know? I just saw the water and wastewater, the demand for water resources engineers, and not just that. You can make a big difference. It's a market that has kind of been ignored, and it's pretty important to have safe drinking water and a clean environment. So I was all in on that. So some pros and cons. Masters can increase your earning potential. I don't think it's going to do that right away, but it certainly didn't for me. I was getting offers very similar to offers I was getting out of MSU, which was kind of frustrating to me at the time. I think it definitely can help you down the road as far as working your way up, and you learn a lot of management skills and stuff like that can definitely help you work your way up quicker. You're building your skill set and knowledge base. Probably the best part, intimate learning with some very bright professors. I remember some days my professors would be missing class at Cornell because, like these are civil engineering professors, but they were basically coders that NASA wanted to know where to put a satellite or something, and they'd say they had to miss class or do it remote. So very smart minds that you get to learn how they think and learn under them. It's a resume builder, and you do get to put off true adulthood for 1-2 more years, which was nice, I guess. Cons, though, you can sometimes feel like you're just paying them to work there because it is way more demanding than undergrad. It almost felt like a job at times. And the high interest student debt can be a killer. It's like 7+% usually. I paid mine down pretty quickly, but for 5 or 6 years, it was $600, $700 a month, and it was tough. Especially at Cornell, it can be more theoretical than practical. Like I did a lot of coding and in MATLAB and theoretical fluid mechanics at Cornell. I tried to stick to more practical stuff as much as I could, but it's hard to avoid. So I think these 1-year MEng programs are getting better at sticking to more practical professional development stuff. Another con is that I think you can learn even more working than going to school, and in that case you're getting paid rather than paying them. So like Dr. Masson's son, he waited till he got a scholarship, whether it be in Australia. You can't really be picky, but I mean, you guys if you are from Michigan, are lucky that you have 2 or 3, I mean, at least 2 very good engineering schools that you can get in-state tuition. I didn't have that option. The Sunie system in New York does not have any strong civil engineering programs. So I don't regret it. I loved my time at Cornell. The debt was tough, but I'm pretty much done with it. And so that's my personal spin on it. This was the coolest part. This is the program I was in at Cornell that attracted me to Cornell, and Agua Clara. So you could see the 19 plants they now have on the graphics on the right, with 17 in Honduras and 2 in India. These are in areas without electricity usually, and they need to be designed to run without electricity, which is, I don't think you'll find a plant in the United States that's running without electricity unless it's some little package plant somewhere. So this is really cool. I'll get more into the design stuff, but the problem was we have 2 billion people worldwide still that don't have access to clean drinking water, and nearly 1,000 children die each day due to water-related diseases, and more than 80% of our wastewater is discharged back into the environment. pretty much untreated. So the rest of the world has a lot of catching up to do. I know Dr. Maston has, I think, done some work in Africa, Tanzania.
Mhm. Yes.
So that's great. It's all great work, helping these communities that, these are people that carry a bucket to a well, a dirty well each day before they got help, and for their whole family, and now they have it on tap. So the mission is to bring these communities safe water on tap. It's growing and growing. They use local construction. Each design is unique, though they do have an all-encompassing design tool online. If you just put in a flow rate, that's what I worked on for them on the design team. And the ability to operate without electricity is huge. So you can see there, I wrote U.S. Treatment plants take up 1/3 of our energy budget and about 4% of our total energy use. So that's significant usage there. So the design of gravity-powered treatment plants, over 65,000 people now. So these plants feature a lot of moving parts, kind of invented by the Agua Clara team through research and innovation that allow for inspection, maintenance, and ease of operation for whoever the plant operator is going to be. Not ease of operation as far as like being able to remote control your plant like a lot of the American plants can now do, but for somewhere without electricity, just being able to, do something with a fitting or a simple valve or baffles. It's basically using smart fluid mechanics and simple, elegant flow controls for the operators. And you don't need that fancy software and electronics that they aren't able to have anyways. I think that the main innovation was a stacked rapid sand filter system, which operate in parallel during filtration and in series during backwash, which eliminates the need for backwash pumps, which is pretty cool. I'll show you that on the next slide. The best part about this was it opened up a different way of thinking for me. You really have to be creative and come up with solutions that are not conventional. You're not just using a clarifier that some sales rep pitched you. You're really boiling it down to the problem and finding the best way to do this without electricity. So on the next slide, I have a few of Agua Clara's key technologies. At least they were a year ago. They moved quickly. Top left is their flocculator. I believe you guys must have done flocculation by now. So they use baffles that are easily removable and replaceable for maintenance. So vertical, the water flows vertically over and beneath these baffles to mix and get and it's very low head loss, and you easily verify the coagulant dose. Then below that is a really cool linear flow orifice meter, which automatically correlates the chlorine or coagulant dose with the flow rate using a float valve attached to that lever arm to the right of it. You see, I worked some on that. And then on the right is the filter I mentioned before. This filter reduces the area required by 1/6 of a conventional sand filter that you would see. So on the left, you see it in filter mode where it's operating in parallel, and then they're able to run it up in series from beneath by opening a 1/2-inch air valve and siphoning air through to backwash and eliminating the need for backwash pumps, which would require electricity. Some slides that I still reference from Agua Clara, I'm just going to run through quickly, maybe to get you guys thinking about flow controls. We'll link them at the end of the presentation. Constant flow, point of use treatment devices. Let's do some quizzing. So if you're adding alum, what treatment process do you guys think that would be for? If we can get some answers in the chat. Let's see who's first. All right. Next, calcium or sodium hypochlorite? Not quite. Chlorite. I'm getting a few softening answers. I believe it's disinfection. There you go. And then sodium carbonate. Sarah and Vincent were close last time.
So for all of you, sodium carbonate, soda ash.
Yeah, sorry, I should have mentioned soda ash. Softening on the brain. Okay, fair enough.
The
pH
homework that's
control,
due this week is on softening.
So why is constant flow desirable for point of use treatment devices? Because you can use a much smaller reactor rather than having some large tank that is designed for the max flow. It's not reasonable to expect to treat drinking water on a demand in a household. So I mean, if you can, the max to average is like could be 100 times. So the system would be idle most of the time, except for peak usage. Instead, Agua Clara's approach is to use a clear well tank of treated water at the headworks so that a supply of treated drinking water is always available. Next, some variable flow control. I like this slide because it uses some useful metaphors with electricity and Ohm's law, basically. So if you think about head, or the energy to push fluid through the flow resistance as the voltage drop, and then you can think of the flow resistance or the resistor, several things you can use: orifice, or small restrictions, porous media like filters do, and or long straight small diameter tube would act as a resistor. So that actually, yeah, the softening was a correct answer there. So then flow rate would be the current there. So I just like that metaphor. I have this full presentation. I think it was the first day of Agua Clara, linked in on the last slide. And you can vary resistance by adjusting a valve as well. So what did I learn from Cornell Agua Clara? Treatment plants should be designed for flexibility and ease of operation so that various conditions can be treated. the ability to bypass or adjust chemical doses as needed, operate at variable flow rates. It's important to have that flexibility. And plants should be adaptable for future growth. Life cycle costs should be considered when considering alternatives. Obviously, it stressed lowering energy and maintenance costs by using smart fluids rather than mechanized equipment that you see in conventional treatment plants. That, you know, if you work in the U.S., you're going to be designing conventional treatment plants for the most part, if that's what you want to go into. But if you can use smart hydraulics and avoid the maintenance and energy costs of pumps and equipment, that is always better if the equipment works. Flow control applications for constant and variable flow. I still think of those slides that I just showed you all the time. It really shifted my thinking from analysis to design, which I'm glad to hear. Dr. Masson says everyone's now required to take one design course in each civil sector, kind of. So that's great, because design is a whole another animal. And then a pro tip is to keep your student ID after graduation. I actually lost mine from MSU, but my Cornell one doesn't have a date on it, so I'm able to use it for discount ski tickets, stuff like that. So just maybe hold on to it. Okay, employment. Since then, I've been with Brinnier and Larios. We're a design consultancy firm based in Kingston, New York, founded by my grandfather in 1956. We're pretty small, 18 employees with 7 engineers, I believe, plus or minus on the 18. About 90% of our work is municipal water, sewer, drainage, and we have a lot of loyal towns and villages that we've been working for you know, since the 50s, 60s. That the other 10%, I'd say, is mainly private site development, which here in New York State can be quite difficult. There's many layers of municipal compliance, approvals required, bureaucracies, a lot of public opposition, whether it's something that they even are for or against. Sometimes these people just fight these projects regardless, and it can be a pain. But it's also some good projects, like, you know, designing some cool car dealerships, apartment complexes, stuff of that nature. Some pros of working for a small firm: the ability to work on a variety of important local projects and the ability to manage entire projects. Some bigger firms, engineers will get pigeonholed into the same type of work each day, where you're just kind of you know, you might be, you know, the water cat guy, or just you're kind of doing the same thing each day. And here, you know, I'm currently working on redesign of our local hospital, some affordable housing projects, stuff that I drive by and get to acknowledge in my local community, which is cool. Some bigger firms will have you designing projects in Colorado when you're working in New York. So, and also, you know, the potential for ownership down the road obviously played a role for me. Cons, lesser resources, learning opportunities, smaller network, I'd say. And I don't have as many contemporaries or competition to push me here because of our size and demographics. But If I had to pick one, I think I prefer the small firm feel. Sometimes I wish I spent a year or two at a larger firm and learned a lot more about how they operate and management and stuff. But I'm happy here. Let's go on to the career path you could take. So like us, there's many design consultancy firms. I'm listing probably the 5 of the top 10 or 20 there. Arcadis, Tetra Tech, I believe, has a Lansing or East Lansing office. These are really good firms for water and wastewater, especially, but they are multidiscipline international firms. There's also, I'm sure, some small firms like us around you. Regulatory, bureaucratic, municipal jobs like EPA, FEMA, DOT. We have the DEC here. I think it's DEQ in Michigan. Department of Health. What's that? Eastern Great Lake. I forget what that actually.
Environment, Great Lakes, and Energy.
Okay, and then the Great Lake Water Authority, Army Corps, Navy, water districts, planning departments. There's a lot of options you can go if you're going into one of these jobs, and these jobs typically have very solid pensions or benefit packages, maybe a little more relaxed than working as a designer. You're probably reviewing a lot of design work. Construction project management is another route. There's a lot of money in this. Seems we do a lot of project management, but there's these big CM firms like Turner is around here that kind of just do construction management, and it seems to be pretty lucrative for those who go that way, or at least it seems so. And then you can be a sales manufacturer's rep and sell equipment to, you'd be pitching, whatever pump or clarifier to design engineers to spec in their designs. So we have people come in all the time for lunch and learns, or just, they'll meet us at a job site and tell us, what their best option is. And they're very helpful because they are engineers that understand it, but they also know their equipment so well that it makes it easier for us. That route, I'd say, is probably more commission based, and you get what you put into it. But I don't know that much about compensation in that world. Academics and research, Dr. Maston would be able to tell you more about this. It kind of involves, if a career in that kind of involves going for a PhD and staying in academics. It seems like a nice gig. Probably pretty hard to land some of these gigs, I'd imagine. But again, I wouldn't quote me on that. And then as an engineering student, you can always pivot. Your problem solving skills, excuse me. Drop my AirPod. Your problem solving skills are in demand. I've saw a lot of people from grad school go work for prestigious management consulting firms, businesses, or go get an MBA, law school. Companies love to hire engineering students, people with analytical problem solving skills. So you're in good shape. Job search, applications, and interviewing. So Indeed, I think, is the best for finding openings. If you're just searching the web, LinkedIn also, you should all be on LinkedIn if you're not already. because if you apply for jobs on LinkedIn, your profile will basically be your application. And then from professors and like, I think there's jobs posted on the blog that Dr. Madison just mentioned, stuff like that, career days, and then word of mouth, honestly. A lot of the best connections come from, you know, just hearing about job openings if you know people, and that can make it easier. But it's a good job market for civil environmental engineers right now. It's much better than it was when I came out. I'd say the median starting salaries raised about 8,000 since 2013, which is nice. Pre-interview, it's very important to research the company you're interviewing at. I'd go on their website, look at their mission, some of their current work and keystone projects, organizational structure, locations, etc. And that way you are prepared and you look prepared, and you kind of want to interview them. I'd say be yourself, interview them too, because your supervisors, whoever you end up working for, it's very important because these are the people that train you, who mold you as a professional. So I'd say choose wisely. And I mean, I wouldn't just take the first job you're offered. And I mean, it depends on your circumstance, but I would choose wisely who you choose to work for, because that's very important. And always send thanks after an interview to anyone that you spoke to. There are some good sites to research salaries, like Glassdoor. Salary Bureau of Labor Statistics is probably the most official one. I pulled this from ASCE yesterday, that the median salary is now $64K. Here in New York, that doesn't get you so far. It's because of the cost of living. But you should always look into cost of living, you know, benefits, and what your role and growth potential would be too. So those are some good tips, I'd say, as far as, you know, engineering seniors trying to find your career path. And there's a lot of jobs available. Here it is. So this is kind of old chart because it was from 2014 projecting to 2024, but it's held pretty true, and it's going to continue to grow because of our aging infrastructure and water and wastewater. Civil and environmental engineers have the highest projected growth rate and, you know, need for employment. You'd like to see the wages grow and the second column, but like I think they have a little bit. There's high job demand in our sector, huge demand in California. You can get paid a lot in California, Texas, Alaska, if you really want to go to Alaska. And then openings near you. I just did a quick search this morning. The city of East Lansing, the state of Michigan, Tetra Tech, which is one of the best firms for water and wastewater, and GPAC all have open jobs in the Lansing area if you are interested in staying around there. These job sites let you search any region you want and use keywords. They make it pretty easy for you to find openings. So working as a design consultant, the path that I chose, time management and tracking is critical. Geez, my AirPods. Time management and tracking is critical in order to properly manage projects and billable hours. So that makes it very important to be resourceful. Basically, if you're not billing hours at a consultancy firm, you're not really getting paid. I've had to eat a lot of hours early on but early on you get your training a lot too. So typically my day, I spend 80–90% of the time in the office, either designing in CAD or writing reports or reviewing others' works as a consultant for towns that we work for. And then 10–20% in the field, inspecting construction projects that I was the design engineer on. So kind of making sure the contractors are following the plans, not breaking any water mains, stuff of that nature. Field experience and understanding construction methods will make you a much better designer. I'm still learning every time I go out in the field. It's good to have a let's go see attitude, ask questions. Don't be afraid to ask questions, because some of these construction workers have 20–30 years experience, and may know how to build it better than you designed it sometimes, and you can learn from that. And then so my typical responsibilities: preparation of plan sets. I'll go through a typical plan set later. Specifications, reports, bid invitations of contractors, reviewing the contractors' equipment submittals, and then reviewing plans and reports by others for towns, and conducting site inspections. And then one last takeaway: I found that water treatment plant and wastewater treatment plant work are by far the most detail-oriented and time-extensive projects. Very detailed process piping, solids and sludge management, equipment sizing. This all requires great attention to detail. And it takes a certain type of engineer, in my opinion. And then we don't really use 3D CAD and BIM. I did in grad school a lot. But these are the jobs where you want it, because you have these, you have to watch out for vertical, horizontal pipe conflicts and fit everything within a process building. So you're going to see a lot more of that in the coming years. All right, so if you remember the first slide, I showed you the 120 billion gallon reservoir that goes down 90 miles to New York City. So this was built in 1905. The reservoir basically flooded out of town. Thousands of acres of farmland and thousands of residents were forced to move. The initial project cost was $12.5 million, which in 2020 equates to $330 million. Seems kind of cheap, honestly. This reservoir provides enough storage to drown Manhattan under 28 feet of water. And the construction required the movement of 8 times as much material as was required for the Great Pyramid of Giza, which was the largest pyramid. So that gives you an idea of the scale. And I thought those were fun facts. So the Catskill and Delaware aqueducts, which you can see on the diagram to the right, they tunnel 500 million gallons a day of raw water 92 miles south to the city and provide 90% of the city's water supply. If you see the red marking just right of the reservoir, that's where I live. And then you have the Catskill and Delaware aqueducts. They do cross at one point. And this is the Catskill aqueduct on the left with the irregular kind of egg-shaped cross section. That's interior diameter 17.5 feet. I think 17 feet in height, and about half of it's buried, half of it above ground. It varies. It's 92 miles. So, and then New York City has a filtration avoidance determination. The EPA waives their Surface Drinking Water Act regulations. The supply subject to the surface water treatment rule. Only disinfection is required. So in order to keep this filtration avoidance, the New York City Department of Environmental Protection, DEP, is required to invest basically millions in the watershed of the reservoir and the wastewater plants in these communities up near me. And it's allowed due to the 60+ day travel time in the aqueduct system. So some recent projects from our firm in water treatment, wastewater treatment. These are conventional treatment practices that kind of limit ability for me to use some of the flow control principles from Agua Clara, though I always try to keep those in mind and try to make ease of operation and cost-effective designs. So the first one, I'll kind of take you through these each separately after. The first one is a replacement of filters to upgrading to microfiltration membranes in the village of New Paltz, which is actually tapped into that Catskill aqueduct, which goes to the city. And this required contingency planning, alternative source evaluation for the scheduled aqueduct shutdowns, which I think are finally over for now. And then we put in Saugerties, a local town, 3 million gallon water treatment plant that existed, but they were having heavy rainfall events in a mountainous watershed. So the reservoir, their raw water reservoir that feeds the water treatment plant would get all this turbid runoff, and the plant would basically have to shut down during high storm events. So we put in a prefiltration tank with tube settlers and a polymer chemical feed system. I'll show you guys that. And then another cool one was the extension of that New York City supply to the Sunie Ulster campus, which is a community college nearby, to replace existing. They had low well yields, poor quality, so it was 2.3 miles of transmission lines and a bridge crossing that I have good pictures of. And that was also aqueduct water. So if you notice, the treatment plant projects are rarely full redesigns, full replacements due to the real world constraints involved. I mean, we're usually looking at replacing, whatever can be afforded to replace or whatever's on the agenda. I've never had really a blank slate where I can just design a plant like I did in 483. You're working with public policy and other constraints. It's usually just retrofits and replacements from all these 1970s treatment plants that are kind of falling apart. So the membrane filters at New Paltz, they had filters in the 90s put in. Oh, that's when the plant was built. And they were not meeting the new 0.2 NTU standard due to entrained air in the aqueduct. They had to replace the filters and fit them within the existing building footprint and without altering the hydraulic profile. So quiz, does anyone know what NTU stands for? It stumped the class last year. So it has to do with turbidity.
We haven't covered filtration yet, so.
Okay. Does Dr. Maston remember?
Nephelometric turbidity.
Yes, it's the Greek for cloudy.
I passed the test.
Last year it was a tough one. Turbidity unit. So that's how we measure turbidity, basically how muddy your water is. So we put in PAL, microfiltration after a 4-week pilot testing of numerous systems. And they're working great. We also put in SCADA controls for remote control, everything NSF approved, which is required on municipal jobs for water. And I already talked about the aqueduct shutdown. So let's go on to, okay, so here's a look at the membrane filtrate, the membrane on the side here, those tubes. And then on the left, it's a little hard to see anything, but that's kind of the overall design. Those were sent from the manufacturer, which is common with us working with the sales manufacturer reps to kind of piece it all together. Build this fog is pre-filtration. So to reduce the high turbid water from the storm events that were feeding the water supply reservoir. It's a very mountainous area around here. We're in the Catskills. So rather than having to shut the plant down during these events, which, you know, this plant feeds the whole town clean water, or the village in this case, we put in this Trident system with the flow diagrams from below, which also included 3 700-gallon per minute tube settlers, sludge recirculation pumps, and an anionic polymer chemical feed system to reduce the turbidity before entering the plant's existing primary filter equipment. So this is usually bypassed, but during high turbid storm events, it is the water's routed to the pre-filter, and then after the pre-filter routed back through the rest of the plant like normal. And it was funded by the Governor's Office of Storm Recovery, GOSER, which is a funding source here in New York that is quite useful. Sometimes it's always good to know where you can get funding for projects. Okay, and then the last one I mentioned was Sunie Ulster. So here's a map showing the 2.3-mile line we had to run, which included easements through private properties, and the agreement to purchase water from this water district that had been established in High Falls. And the result was a new reliable source for the campus, and the new water main was connected to a 110-gallon bolted steel water tank on campus that can feed the campus distribution by gravity. So there's the new tank on the right. Statewide Aqua store is a major player in the steel tanks. And then on the left is the, we had to cross the Rondout Creek to do this. And that's a lot harder than it looks. That's below a road bridge, ductile iron, Agua jacketed insulated bridge crossing. And so I thought that was pretty cool to show. That was just last year. So some trends in water and wastewater treatment. Yeah, aging infrastructure. We've been saying this forever, but a lot of the plants from the Clean Water Act in the 70s are needing to be replaced, retrofitted, and then our distribution systems, even older than that, are troublesome. And you have higher water usage. So climate change. You have more severe storm events. You have the droughts and fires out west, temperature rise, sea rise, saltwater intrusion. This is all affecting our approaches to water and wastewater treatment. You're seeing desalinization used more frequently where there's saltwater intrusion. Population growth is just, going to increase water demand. There's a lot of mergers and acquisitions in this market in the last 5 to 10 years. Bigger firms buying up smaller firms like us to get a bigger market share. Going on a lot around here. Low pressure sewer systems. You guys probably don't know about yet, but those are at individual pump stations at each house rather than a septic tank when you don't have a lot of gravity to work with are really useful systems. We've been putting in a lot of them. Internet of Things, real-time sensoring, monitoring that allow rapid responses by operators. This is the SCADA system, SCADA is usually used. That's kind of what I'm showing with that diagram there. So there was I think in Texas, where did I put this? Earlier this year, I think 8 months ago, there was the thing about this is that it was hacked, I think from a foreign country, and they increased the dose of sodium hydroxide from 11 parts per million to 11,000 parts per million remotely by a hacker. So luckily the plant operator saw it immediately and was able to shut it down because this was basically drain cleaner that was going to be was going to kill people if it got into the distribution system. So the ability to remote control and have rapid response is really makes it easier for the plant operators to see what's going on at their pump stations, even the plants when they're not there. Another trend, funny enough, is the use of flushable wipes is clogging up all of our sewer pump stations pretty much. So we've been replacing them with some heavy duty grinder pumps all over the place. And then, water resources engineers are in demand. The job market appears to be excellent, and the wages are solid right now. So you guys are in good shape as far as that. Now some advice, some topics, items this class doesn't have time to address maybe. I mean, working with manufacturers and suppliers, like I said, this is a large part of plant design, as well as on other projects. So it's good to become familiar with their products and their reps, because they're very helpful. They'll send you CAD drawings of their equipment that you have to work into your plan sets. Metric, I know Dr. Maston loves it. She's an academic, but if you're not academic, non-international practice, I haven't used metric system since it wasn't on the PE exam. I know she hopes we'll switch over someday.
When I was in 3rd grade, they said we were going to switch over within another couple of years.
Yeah, my dad said that too, and then they never
did.
I don't think they ever will, but it would be nice given how much better the metric system is, but we're used to gallons and feet now. Groundwater, stormwater treatment, I do a lot of this stuff, and design of subsurface disposal and septic systems. Those are smaller systems. Once you know how to design wastewater treatment plants, you're going to be able to pick this stuff up. Process and plant design will require the combination of treatment topics in this class and principles from 422, which is a class in the spring, I believe. I was talking about hydraulic grade line before, and hydraulics, so that you have to really track the hydraulics through the plant to optimize your unit processes that you learn to design. Oh, hydraulics is concurrent. Okay. That's a great course. I don't know who teaches it now, but I really enjoyed it. And then spending time in the field and understanding construction methods, again, crucial to becoming a better designer. I've become familiar with valve fitting types and applications, other construction materials. Well, I was talking about hydraulics. Let me see. Okay. Here is a WaterCAD model of the village of New Paltz. So they tap into the aqueduct, and then everything comes to a reservoir. Are you guys seeing this? Reservoir here, pressure reducing valve, and then down into the system. I had to place demands at each node based on billing data from the town provided me with, elevations and demands. And you can do fire flow scenarios and, master planning purposes to see if you want to put in a tank. Here is their actual tank that we designed, and you set the operating levels, and it really helps these towns plan improvements and master plan for our larger capital projects. So I built this based on their mapping and their data, and I've done this for a few towns. It's a good tool. Oh, and also there was a plan set. This is a treatment plant I designed that they withdrew their application during COVID, but we were abandoning an old plant, and I actually did get a fresh slate on this one pretty much, which is rare. Let's see if so here's a hydraulic profile tracking the grade line, the ground elevation, and the invert elevations through the plant, through each of the, septic tanks, splitter boxes, RBCs, which is, you guys haven't gotten to a lot of this stuff yet, but you will. So that's what a hydraulic profile looks like. And our typical plant sets are 15, this one's 25 sheets. So there's a grading plan. I do a lot of that. And then this stuff, this is the equipment that a lot of it is coming from. Well, here's a schematic showing you the plant, and then equipment. Here's our RBCs and our filter building, and pretty much all the precast concrete required. And it takes a while in CAD to put these together, but it's nice when you get them in and get them approved by DEC. One thing I will say, COVID did disrupt the state agency approvals. Really were held back because they basically shut down DEC during all of this. So I wasn't able to, we were just sitting around waiting for approvals, but they're kind of back. And other than that, I guess private projects, a lot of people stalled, but COVID, we were pretty resilient through. And here is to show you how I save my work. This is a metric system, and this is my 483 project for Red Cedar Engineering, which is a fake firm, obviously. And there was a softening plant with lime and soda ash. And I think it was really well done for a 21-year-old, but we even got the rooms for labs, restrooms. I mean, come on, Dr. Maston.
I agree. It's
I,
awesome.
I don't even think I got 100 on this. So, anyways, next slide. Some more advice that I had given myself when I was in your class in 483. Be a skeptic, critical thinker. Don't be afraid to ask any question. Bring up new ways of thinking. Question empirical methods, conventional methods, even if they're widely accepted. Avoid student debt if possible. I touched on that on grad school. That can be crippling. Always continue to learn and enhance your skill set. I've been learning ArcGIS for 2 years now, but I don't have that much time. Landscape architecture, anything that merges with my field, I like to learn about. It's just tough to find time, but you do have professional development. I personally have invested in water and agriculture stocks long term. Water is not priced like oil. People think of it as free, but it's really very important. And I think in the future it will be priced like a commodity and valued as it should be. So I think those are good investments once you have some income to work with. The PE exam. So I took the FE exam. I didn't have a chance to study for it because our capstone was due the day before or something, but I was so used to solving problem sets every week, for 4 years that I cruised through it. I think they give you 4 hours in the morning and 4 in the afternoon for both the FE and PE. So for the FE, I took 2 hours and 2 hours, never even thought about it. They give you an equation book and I just cruised through it. And passed. And then the PE exam. So I used to pride myself on my test taking, and I might have gotten a little cocky. The PE, I didn't start studying until very late, and I didn't realize I didn't have the civil engineering reference manual, which is right here, made by Lindeberg. I was like the only one in the room of 500 people without the book. I was flipping through like 20 different books and I was running out of time. And so I failed the PE my first time. But that is, that's where we learn from our mistakes. So I took it again. Obviously, I had the book this time. And I passed the second try. I found it much harder than the FE, maybe because I wasn't used to solving problem sets every night. Yes, PE is now computerized. Neither were computerized for me. So I don't know what that's like. And Dr. Maston can maybe provide I know she had a colleague or a TA that had trouble with taking the environmental instead of the civil or something. So one can take the PE, right? No, you can't take the PE until you have 4 or 5 years.
In Michigan, you can now. You
What?
can actually, you can't get licensed until you've got the 4 years experience.
Oh, that's
great. But you
great.
can actually take the PE exam. In fact, we had one student that actually took, because of scheduling during COVID, actually took the PE before she took the FE.
Now that seems ridiculous, but I like that. I wish I could have done that because I would have cruised through it.
I mean, my advice is to if you're in Michigan, take it right away. because you are used to.
Yes, it's way different. I was so much quicker with just simple, like, solving series of equations that I used to do in 5 seconds takes me 20 seconds. Now you just don't. I have proprietary software that calculates stuff for me now. I'm not really writing out my solutions like I was on homework. So if you guys in Michigan have that ability, I totally suggest taking them both right right after your senior year. I mean, I can't see why not. That's amazing. If you want to be a PE, but if you're not going to be in Michigan, I would suggest buying this book early, not just like when you're going to start studying, but even like you could buy it. You could buy it now, and it's a great reference. I use it all the time now. But learning the book is a huge part of navigating that exam.
Except not anymore because it's online.
Yeah, but
So,
it's
so now with the civil exam is still a paper and pencil exam. The environmental exam, PE exam, is also online, just to at least in Michigan. And so the NCEES environmental exam is online, and the only thing you get is the reference handbook.
okay.
So
Well, that
it's a
makes it
different
even easier.
it's a different reference handbook than for the FE exam, but that's all you get is the reference handbook.
Okay, well, that's great because though, I mean, the FE reference handbook was very easy to navigate and much smaller. I mean, people were showing up to the PE with 2 suitcases full of books. I mean, so
I did.
yeah. So times are changing. I mean, where I work here at the time, I was the only young engineer here, so everyone who had taken it took it when it was a partial credit test, more like homework set rather than now it's 80 multiple choice. So it kind of changed a lot. Now I'm hearing all this stuff about the environmental in Michigan, and it sounds like it's gotten easier that way. So that's nice. I would take advantage of that while you're in Michigan if anyone was planning on leaving, because it's usually pretty easy. I took my FE in Michigan and easily got it transferred to New York. Next, become familiar with available resources, environmental mappers, web soil survey, stream stats by USGS, all the relevant design standards and manuals you'll need, modeling softwares. Google Earth is great sometimes, LiDAR, parcel maps, precipitation data. And there's some cool apps like for construction management, FieldWorks, and then Canvas is a cool app that I just discovered recently. A lot of realtors use it for like 3D walkthroughs, but I've been using it like at pump stations, and you get like the full 3D rendering, and you can send it right into CAD. So that's all part of being resourceful, and also being resourceful is saving time by reusing work. So we have a lot of standard CAD details, templates, old cost estimates that we can work off of that from other projects in the past that when they're applicable can save us a lot of time and help us save our clients money and save everybody money. And then one last thing, I think this is the best commencement speech. It's called "This is Water." I think it's probably one of the best things you can hear, like as a senior in college. I've linked it in one of my final slides by the late author David Foster Wallace at Kenyon College in like 2005. But really helps with self-awareness and getting out of your natural default setting and getting off your phones. I added that part. One last advice slide: track and bill time effectively and ethically. Be honest with supervisors, clients, and don't make promises you can't keep. So I know course objective is to learn the ASC ethical canons. I think this hits on a few of them. To not misrepresent your work. I don't have them in front of me. If any project or issue is even thought to be a potential ethical issue, I'd speak with a coworker or someone you trust before going ahead. Keep records, files on all projects and coursework if you don't already. Like I just showed you, I still have my 483 design. I have files on everything pretty much. Don't try to do it all on your own. So I did that a lot in college, but working together and learning to work on a team is huge, and it's great for ensuring quality, QA, QC, quality assurance, and coordination. That's a big part of working at a firm. And then try to get along with all types of people. This is an invaluable skill. Avoid holding grudges, be aware of others' backgrounds and motives, have a sense of humor, and be thoughtful. So, I mean, this is something I think I've learned from watching my dad. He gets along with everyone, and it's not going to do you anything but good in the future. I mean, if you leave a firm, you should still have good relations. I wouldn't go cursing anyone out, because you never know, who you're going to cross paths with again. So that's just a good outlook to have. Be willing to take responsibility for the whole team, even if it wasn't your fault. I think that's a great attitude to have. Project management. If you're in construction, engineering, you'll learn this. That triangle, scope, schedule, budget are the three keys there. Be careful. Try to think of audience and consequences before speaking. I also noticed this when at planning board meetings and stuff. Sometimes I used to think, my dad would be elaborating or something and telling a story slow, but really I realize now he's just thinking of all the potential, any potential audience or consequence that could come from this, and framing his words in the best possible way. So that's something I've learned. And then self-analyze your performance and progress towards goals. I think it's important to set personal goals for you to continue to grow. So I would, whether it's a spreadsheet or just an index card, which I use, I just, every year, 6 months, I try to, set personal goals, not even just work related, but fitness or diet related, and hold yourself accountable. Okay, we're close. Sorry if I'm going long. All right, Spartans will set lofty goals and work towards them, solve one problem, and then move on to the next. So here's some Spartans who have shaped the world. Dare to dream. We got a lot here. We got the E. coli experiment from Richard Lenski. Rosalind Franklin helped Watson and Crick discover the double helix. Alfred Hershey won the Nobel Prize in Medicine for discovery of replication of viruses to genetic structures. Dan Gilbert, there's a few professional sports owners. Dan Gilbert from Quicken Loans is still very involved in Michigan State as a booster. And Lyman Briggs, I think you guys recognize the name, was the third director of the National Bureau of Standards, chairman of the uranium committee pre-World War II. Studied soil mechanics and moisture at USDA. So I think you guys probably took soil mechanics, and received the Medal of Merit from President Truman. So that's a really good Spartan there. John Hanna, his statute on campus, longest serving MSU president who turned it from Michigan State College to the research university it is today. Served as head of the U.S. Agency of International Development and was the first chairman of the U.S. Commission on Civil Rights. Jim Delegati invented the Big Mac. He's a Spartan. Judith Vedder, Boeing, retired Lieutenant General for the Air Force. Magic Johnson, speaks for himself. Draymond Green, Kirk Cousins, Le'Veon Bell, those were my guys. So I went to college with them 3 out of my 4 years, and they're all great professional athletes now. So that was fun. And then our esteemed professor here, I didn't want to shorter any publications or awards, so I just wrote dozens. She's in some good company on this slide. And then which one of you will be next? You know, dream big, I'd say. And then last slide, here's a quote from JFK I included last year. I think it's from the 60s, but obviously still relevant. Anyone who could solve the problems of water will be worthy of 2 Nobel Prizes, one for peace and one for science. And I think, you know, most of the world's still trying to solve that. And, you know, in the US, still, we haven't quite solved it. So I thought that was a powerful quote. So thank you for your attention. If you guys have any questions, I can answer them now. You can email me. You can connect on LinkedIn. I'm always willing to help fellow Spartans, job search stuff, any career advice. I'd be happy to help. And here are some links that I promised.
Thank you so much, Paul.